Okay, sure. Okay, so in chapter 1, we've learned about the different biomolecules that you can find in biological systems. We have proteins, we have carbohydrates, we have nucleic acids, and of course we have fats. So there are four basic biomolecules that we can find in biological systems. And those biomolecules are, of course, organic compounds. And if you look at the biomolecules, no, there is most often there is always a chiral center. In your organic chemistry, you've learned what is a chiral center with the atom is banded to four different groups of atoms. No, expect your atom to be chiral. No, and because of that, chiral center would lead to different orientation in space, no, that would have different configuration. And biological systems, receptors in biological systems are very specific that it would only choose a very specific orientation in space, no. For example, in proteins, for amino acids and the basic components of proteins, the amino acids, you can only see one particular orientation of the amino acid having an L stereochemistry. Okay, that is similar to what you see in L-glutaraldehyde. In the L amino acid, you have this kind of orientation. So when you draw on the three-dimensional 3D version of the amino acids, we really have to specify such as this. So you have a wedge and you have a broken line. Okay, you have a broken line. The broken line is oriented away from you and the wedge is oriented towards you. That's how it is being depicted. So if you have something like this, like a T shape, the one that is vertical is oriented away from you and horizontal is oriented towards you. And any changes of that orientation in space would lead to a different stereochemistry, although the rather connectivity is the same. So you call this one as stereoisomers. One is an L and the other is the D. So they can be called constitutional isomers because they are connected in the same manner. But the only difference is the orientation in space. So now let's go back to, in particular, to the proteins, one particular type of biomolecules, and we have learned that proteins, what made up proteins are the amino acids. And there are 20 standard amino acids, and all they are in the L form, standard amino acids, and we can cluster them based on their side chain structure. The general structure of your amino acids R. You have your R. The difference in the side chain would lead you to the different 20 standard amino acids. There are only 20 standard amino acids you can usually find in biological systems. So any changes in R, we start with the smallest one, which is the R equivalent to H. And when R is equivalent to H, we actually find glycine. This is the smallest. When R is CH3, you have the alanine. So, and those 20 amino acids can also be a group, no? They are polar and charged, passively charged, negatively charged amino acids. So, polar, usually, if they have OH, no, or SH, COO, or NH2. If you find COH, another COH can also be considered polar, no, but usually these are the polar and charged amino acids. They can also be classified aromatic. You can see their ring. For aromatic amino acid, the easiest way of detecting them is through the UV spectrometer, where you can find some certain absorption of those aromatic rings of the amino acid. Then you can also find positively charged amino acids, where you find an amine group that is being charged. And then negatively charged amino acids usually can have COOH that is deprotonated. When I say deprotonated, the hydrogen is removed, that you can only see a negatively charged on COO. Now, for those who ask what is the COO, COO is simply C double bond OO. This is from the carboxylic acid group, no? But however, the hydrogen is removed, so one of the oxygen will be negatively charged. So carbon is bonded to 4 bonds. You have 1 bond from this carbon and 2 bonds from oxygen, C double bond O and CO. Okay, so that's 1, 2, 3, 4. And the 4th one is the O. This one is the shortcut now of writing your COOH. So each amino acid has an isoelectric point. What is that isoelectric point? It is the point at which the amino acid in its structure in solution is neutral. And you can also have, neutral, you can also classify your amino acid to be, aside from being non-polar, no, where you see all the, you don't see any polar groups, you don't see any OH or CH3 or amine or COH on the R chain, but you just see carbon, 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 no, and then a small C, so forth. It's not very polar. So that's the basic you can find with non-polar amino acid. When say polar again, when you have your OH in the end, no, or C double bond O NH2, because this can form hydrogen bonds when you have an OH group in the R side chain. And you can also consider your amino acids to be polar, pag na siya COOH. And this one, for polar amino acids, this is the same as classifying them into negatively charged, because in solution, this carboxylic acid here in the side chain are deprotonated, which means the C double bond OOH, the hydrogen is removed, where you can only find a negatively charged side chain here. So those polar amino acids are also considered to be negatively charged. And then we have the polar basic amino acids. You have the amines. You find NH2, NH2, or the cyclic NH aromatic cyclic amine. Now you have the NH, and in solution again, these amine are protonated, which means that they are positively charged. So these are the basic amino acids. Why man? I have seen you the reaction before, no, when the NH or when the NH2 or the NH, okay, will react with water. It will react with proton, because there is a, to react with proton, and then you produce plus water, you'll produce actually an OH in solution. That's what make it basic. And when it reacts with water, it becomes positively charged. For polar amino acid, the COH, when it reacts with water, water will obstruct the hydrogen here. So it will get the product in the reaction with water, it will get H3O plus, or simply the hydronium ion, or the proton or the solvated H plus, no? So which means your solution is acidic. If you remember your general chemistry, if you get into the acid-base, no, reactions, and you will actually produce hydronium ion in solution, no? And that's what make it acidic. Again, for acidic amino acids, you expect this N to be negatively charged, the one that I have shown earlier. And this one, you expect to be the polar basic amino acid, you expect to be positively charged. So it is also possible, in particular for cysteine. Your cysteine is the one with the EI in E. Now this is one of the 20 amino acids, basic amino acid, common amino acid, but it can also undergo reaction with each other to form peptide, a disulfide bond composed of 2 cysteine amino acids you call cysteine, with minus E in the cysteine. This is an oxidation reduction reaction where you can find a disulfide bond. This kind of reaction is similar to the reaction when you do hair pakulot, no? pakulot nga style, no? Because the proteins in your hair, the amino acids in your hair, could undergo oxidation reaction to form disulfide bond. You can have this. And also when you go straight sa hair, no? It's also a redox reaction. Of course, we know our hair is made up of keratin. It's a protein, and proteins are made up of amino acids. So aside from the 20 standard amino acid, it's also possible to have non-standard amino acid modified, which means that they can be synthesized in the lab. No example, or sometimes there are biological systems that we can find the non-standard amino acids, but not all the time. So these are some of the example. But so what you will be looking, why would you consider them to be an amino acid? You simply have to look at the structure that has the carbon and the COOH. This one, the carbon, the alpha carbon, the COOH, and the NH2, and of course the hydrogen. Okay, and then this one is considered to be the R group. And you will see this in the structure. It seems like a glutamate, but with a change in here. It seems like a proline. Okay, isa-isahan na to na proline. Asam na si proline. Okay, you can have your proline. Let's go back to glutamine or glutamic. Yes, the glutamic acid. You have CH2, CH2, COOH. Now you can find here CH2, dapat CH2, CH2, COOH here. But you can find that instead of hydrogen, CH2 here for glutamic acid, let's focus on glutamic. This one, no, the polar acidic amino acid. Here, the glutamic acid, you have C, COOH. This is your basic structure of the amino acid, the three groups, which is the COOH, NH2, and hydrogen. No? In this case, this is not in the Zweiter ionic form. This one is your R group, and you will see that you have CH2, CH2, C double bond OOH. No? So, duha ka CH2 and COOH, but you will notice that the CH, the hydrogen here is replaced with COOH or COO minus, depending on the pH of the solution. So that's why it's named as carboxyglutamate. Also, this is derived from proline, no? The chains lang siya. So look at the structure of proline. There is a proline here. You have carbon, hydrogen, your NH2, supposedly COH, but it's a cyclic one. So you have CH2, CH2, all are CH2, CH2. That's the ring, no? When you look at here, you'll have in CH, NH, COH, no, NH2, CH, COOH, and you have CH2, dapat CH2, CH2, but this, the hydrogen is replaced with OH. So we consider this to be a variation of proline, which is we called 4-hydroxyproline. Okay. Also, last time we learned that in solution, the amino acids are charged. When we say charged, they are ionized in solution. And what in solution, they actually exist as Whiter ionic forms like this one. The amino group is protonated, which means the amine, when it accepts hydrogen from water, it becomes NH3 plus. And the COH, when it reacts with water, it becomes COO minus. Okay, and this is what we call as Whiter ionic form. What when we don't see COO minus or NH3 in this form, we call this a non-ionic form. But again, I have to emphasize that this non-ionic form is non-existent in biological system. They don't exist in this form because ideally or in reality, this amino group will react with water to form NH3 again and COH to form to react with water to have this negatively charged form. Now, when considering Now, aside from that, no, you can also consider your amino acid to be amphoteric or ampholytes, which means that they can act as an acid, they can act as a base. No, so when they act as an acid, no, it accepts protons. It can dissociate to form protons, and you will have this form. And if it can act as a base, it will accepts proton to form this form. If it acts as an acid, it donates proton in the solution. Therein his definition of acid. An acid is a substance that dissociates to form H plus or hydronium ions. When we're running out of time, please just click on again the link that I sent you and start the meeting again. So again, your amino acid can act as an acid. It dissociates to form hydronium ion or H plus, and it can accept H plus, and therefore it can act as a base. So you have this form. When your amino acid charge in solution is 0, okay, then you can have your amino acid to be in its zwitterionic form, which is in its isoelectric point. Now, basically, if you have a neutral pH of the solution, let's just say neutral solution, and all the charges in the amino acid is 0, okay, considering also the side chain. When we add hydroxide solution, now what happens is you can have a basic solution. This is what we've learned last time, and we expect when we add basic solution, then the net charge of the amino acid is negative. Nga naman, the hydroxide will abstract the hydrogen here, and you will have the net charge to be negatively charged. So at the pH higher than its neutral form or uncharged form, the net charge at the basic solution is negatively charged. When we add some acid from the neutral solution, what will happen is the net charge, so you lower the pH, and the net charge will be positively charged. Okay, now let's consider, for example, if the neutral solution or the net charge of the amino acid is not in the neutral solution, pH 7, so it will depend now on its isoelectric point. Now, if it's the isoelectric point is not 7, okay, it is the point at which the amino acid has a net charge of 0. So you will have to base on the isoelectric point of your amino acid, okay? So the pH higher than this, for example, the PI or the isoelectric point of your amino acid is 5.97. When we increase the pH, a little bit of this, so let's say a pH higher than 5.97, let's say pH 7, no, the net charge, although the pH is 7, like almost like neutral, but since at pH 7, it's already higher than the isoelectric point, the point at which all the charge is 0, the net charge of the amino acid is 0. So you expect the structure of the amino acid to have a net charge of negative. So which means when you look at the amino group, it's neutral, but the carboxylic acid is negative. When we lower the pH from the PI 5.97, okay, you expect the net charge to be positive. Okay, so your point will always be the isoelectric point. No, not all amino acids would have an isoelectric point of 7. Okay. So this is just an example, and you always have to refer to the isoelectric point of the amino acid. So amino acids can react, no, to form proteins, of course. So here is an example of the reaction of your amino acid reactions, no. So you have this reactant here, and you have your CO to form the acetylbanone. We'll focus on here. This is some of the examples. So how do we form proteins? So we form proteins by the amino acid, different amino acid combination or reactions with each other. And for them to form again, a peptide bond is being utilized, or a peptide bond is formed when the reaction occurs. So the peptide bond occurs from the carboxylic group of the first amino acid and the amine group of the second amino acid to form a peptide bond. So C double bond O and H, and this is what we call as the peptide bond. In the process, the water is removed when a peptide bond is formed. And so a peptide bond is simply the C double bond O and H, and this one is simply, if you look at the functional groups in functional groups or by functional groups, classes of organic compounds, no, this is simply an amide class of organic compounds. So the amide bond, you will see that C double bond O and H, and carbon is bonded to three groups of atoms. Now we will see later on the properties. Again, so in reality, no, you expect your amino acids to be zwitterionic, to be in zwitterionic form. Okay, so you expect can write your amino acid in the already in ionic form, COO, O minus, and H3 plus here. Okay, so when they react, so you have the carboxylic. When you write, by the way, when you write now, make sure that the amino group from the left side is written here, and the right side is the carboxylic, because when we form the peptides, we write from the N terminus, the amino acid form terminus to, or amino form, the amine form, and the right side will be the carboxylic. And so you write starting with NH3 plus on the left, and the right is the carboxylic group here. So here is written, see here is written, this one is written in neutral form or non-ionic form. So here we write in ionic form. So we remove this O here, and of course, and the hydrogen also here. So what happens is that you will have C double bond O that's maintained. You remove the O here, and you form a bond here to the two H2O, the two hydrogen here is removed, and you have an H. In the process again, what is removed is water. Okay, so maglibog mo, just remove the O and two hydrogens, the water. If you have this form, you also have removed the OH and the hydrogen here, you get H2O, the water. Here you also get O2 here, two hydrogens, and the O here, you get minus the H2O. Okay, you get the C double bond O maintained, and then just form a bond here to get your NH. Okay, so amino acid, amino group with the carboxylic group of the first amino acid and the amino group of the second amino acid, you form a bond here, the C-N bond, and you will have your dipeptides, two peptides here, two amino acids here. You consider that to be a dipeptide. So what you form, this one is the basis of your peptide bond or your peptide bond. Okay, so where is the peptide bond formed? The peptide bond is between the carbon and the nitrogen carbon of the carboxylic acid of the first amino acid and the nitrogen or the amino group of the second amino acid. In reality, this one is linked to the C double bond O and H. No, this whole thing is considered to be an amide bond, this one. But what is newly formed is simply the carbon and the nitrogen bond. But if you consider since this bond is connected to this carbonyl carbon here, the C double bond O carbon and the NH. So when we consider this, is already considered as an amide bond. And that is our peptide bond, since this one is part of the properties of the amide bond. So the peptide bond is also an amide bond. But what is newly formed is simply the carbon, nitrogen, this one. But since again, this is connected to the C double bond O, when you look at the overall functional group here, this is simply, you don't consider this to be an NH lang or CO lang, C double bond O lang. But since they are connected to each other, we look at this as the whole group of atoms, a new functional group called the amide functional group, and that is now our peptide bond. Now, when there are two amino acids that's being formed, no, you consider that, oh, there's only one peptide bond, but since there are two amino acids, you consider this to be a dipeptide. I repeat, even if there is one amide bond that's being formed, but this is composed of two amino acids, so you call this one is a dipeptide bond. But how many peptide bonds there are? There's only one, but since there are two amino acids, you consider this to be a dipeptide. Okay, so again, the poly